This is Chapter 20, Part 3 of the notes. We're picking up talking about batteries and redox reactions. So we've talked a lot about redox reactions, and then they occur when electrons are transferred. Batteries are a great example of this, how we've harnessed redox reactions in order to store electricity. So batteries are voltaic cells that used the natural flow of electrons from a redox reaction for energy. Okay, remember, flowing electrons is electricity. So here's an example of a voltaic cell that you might set up in the lab, and we took a look at one of these in our virtual lab. So we have two electrodes, two pieces of metal, and we have two solutions. Okay, so when we place these in solution, we have one side that's going to be reduced. So we have a copper solution here, and we have a copper electrode, and then we have a zinc solution and a zinc electrode. So the zinc is going to be oxidized, so it's giving up its electrons and it's going into solution. So if we look, the electrons are going to travel through, and that's where we get this voltmeters measuring the electricity. And here the copper is going to be reduced, so it's going to receive those electrons and form. Notice the electrodes here. Zinc has been eaten away and it's gone into solution, and then copper has built up because it's coming from solution to the electrode. The salt bridge is added so that we don't get a buildup of charge on either side. It allows just the ions, the charges, to move from one side, but not the actual solutions. All right, parts. Oxidizing solution. So zinc is going from a zinc metal to a zinc ion. And reduced solution. Okay, copper is going from the solution onto the electrode, and there we have our metal electrodes, and we have our salt bridge. Okay, now we have special names for these electrodes. We call them the cathode. This is the electrode that is in the side being reduced, so this would be our cathode, where the reduction is happening, and the anode is in the side of the oxidizing reaction. Okay. How can we use these voltaic cells in everyday life? Well, that's easy. We use them in batteries. Taking voltaic cells and make them easier to carry around. So obviously it'd be really hard to carry a couple beakers and a salt bridge and electrodes in your pocket, but we could put these in a nice compact battery. And they use the same procedure, except they don't use a liquid, they use paste. That's why we call them dry cells. So let's talk a little bit more about these dry cells. So two major types that we're going to talk about: the lead storage battery. These are the type we find in cars, and here's the dry cell that we find in most things. So instead of using solutions like the voltaic cell in the lab did, we use a paste. It's a lot easier to carry around, more concentrated, easier to use. And we have a really special design. So we have the cathode, so this is the metal that's going to be reduced, and we have the anode as a shell around the paste, and we have the paste in the middle. It's going to act as an electrolyte, allow charges to flow. And what happens is the same redox reaction. The cathode is going to be the cathode is going to be reduced, and the outside is going to be oxidized. And when that reaction happens inside, guess what? Then we have electricity flowing. But the beauty of this is it doesn't happen unless these two sides of the battery are connected. Once those electrons have somewhere to flow, then the reaction happens. And when the reaction is all used up, the battery is dead. We do have rechargeable batteries, so like a car battery, which allows it to reverse. If you add electrical current, you can reverse the reaction. But here it's a little bit different. We have overall electrolyte solution of, this is sulfuric acid, so we have a really dangerous acid. That's why you don't want to get this stuff on your hands. Okay, we have an acid inside the battery that allows those charges to move. We have a lead grid, which acts as our anode, and then we have a cathode made of lead oxide. Okay, and again, once these electrons have a place to flow, then that electricity flows through, the reaction happens. And again, these are rechargeable, so when you run your car, you actually reverse the reaction, okay? But your batteries can go dead, okay, if you leave your lights on, something like that. But they are reversible. That's the nice part about car batteries. How does our lab link to corrosion? So we did that virtual lab. Corrosion is a process of returning metals to their natural state. Okay, so corrosion is when metals are reacting with the oxygen, right? So we can see we have rusting form. It's a redox reaction. So we have iron metal, Fe, reacts with oxygen to create iron oxide, and they're exchanging their electrons. Lots of metals corrode, but not all of them corrode the same. For example, aluminum. Aluminum will be oxidized by the air, so aluminum reacts with oxygen to make aluminum oxide. A thin layer of aluminum oxide will cover the metal and protect it from further corrosion. So unlike iron, which just keeps rusting away, aluminum just gets a nice thin layer and then it stops corroding. That's why it's pretty nice to use. Okay. The next thing, when we're using these metals in the environment, we have to figure out how to stop them from corroding. And the activity series comes in handy for this. So one of the ways we do that, we have a buried pipe here, and it's prone to corrosion. By connecting it to a wire to a container of magnesium, we stop the iron from corroding. And my question is why? Why would that stop the corrosion from happening? Well, if we take a look at our activity series, iron is right here. Okay, iron is right here. And magnesium is way up here. So if they're higher on the activity series, it means magnesium is more reactive than iron, meaning that any reaction that starts happening here is actually going to cause this to react instead of the iron pipe. So if we put it next to a more reactive metal, the more reactive metal is actually going to react. All right, last thing we'll talk about, those lead storage batteries have a high advantage. They can work for several years in extreme temperatures, provide a lot of voltage, and they can recharge. Okay, where do we see these lead batteries? In cars. So that's it for our redox reaction chapter notes. We're going to end here, and we'll see you in class.